let me ask John to come to the podium. Now I will have to introduce you Professor John Holland. And let me start my introduction with one thing which we heard yesterday. Per Roland showed a black and white snapshot of an old German scientist, Hermann von Helmholtz, who looked very tired because he wrote a long book according to Per. Please take a seat, John. And I am happy to announce to you that Hermann von Helmholtz's great-great-great-grandson is here with us today. Do you know that, John?
No.
Yes. I checked in the mathematical genealogy website who are your ancestors. And you are the great-great-great-grandson of Hermann von Helmholtz, whose student was Wundt, the very famous psychologist, the father of experimental psychology, and you are the great-great-grandson of Wundt. So I am happy to announce that.
But we know there are only 6 steps between any person.
Exactly, exactly. And then there is one more funny thing. So, you know, John is Mr. Algorithm. He got his PhD. He studied physics first, then studied mathematics, and then he got his PhD in 1957, the very first PhD in the world in computer science. And it was the year when John von Neumann died. So I wonder if you are not the reincarnation of John. Anyway, I don't think I have to introduce John. John is, John. We should know. He's a mathematician, a physicist, a psychologist, an electric engineer. He is very famous for the generic algorithm. He's very famous for his books on evolution, emergentism, many, many ideas. So he is a living institution, just like Jean-Pierre. And let me give the word to this living institution now.
Can I just leave the mic?
I think so.
Yeah, that would be, I just do not carry it. Is there a pointer, though?
Pointer.
Let me start by this very standard diagram so that we have at least similar terminology. We've got the body of the neuron, we've got the axon, and one thing to really keep in mind is every single neuron touches about 10,000 other neurons. So if we go now to the next slide.
Is this one?
Oh, great, great, okay. So if I just press this, okay.
I press it for you. You say
Oh,
next
all
slide.
right.
Okay.
So the thing we want to talk about, or that I want to talk about, is the number of loops in the central nervous system.
Next.
Okay, if we look at the neocortex, good idea. If we look at the neocortex, we see that we have approximately 500,000 columns with 70,000 neurons in the columns, okay? And if I look at the bottom of that slide, a piece of cortex the size of a grain of salt contains 680 fibers and 774 synapses. Now, because there are 1,000 or more synapses per neuron, and this is the key point, all possible loops defined by selecting neurons 2 at a time, 3 at a time, up to length 25. So all possible paths, all possible loops that I could have of length 25 or so will be present there. There, yeah, thank you. Now, the point is that if I start talking about consciousness, it's these loops that allow things to be kept in mind, to tried out, to do planning, the kinds of things that we expect of a human, to look ahead, look at alternatives, try alternatives. All that depends on the number of loops. And what I've drawn at the bottom there are the kinds of loops that I could have 3 at a time, 4 at a time, 5 at a time, and so on. The point you want to keep in mind here is that all these loops, up to about 25, length 25, are present in the neocortex. Okay. Now, these are properties of neurons that are not typically talked about very much. The neurons have a time-varying threshold. Threshold is not fixed. The longer it is between times that a neuron fires, the easier it is to fire it. So neurons are sitting there sort of waiting to be fired. And if you ignore them for a long time, then eventually they will fire on their own. Another thing is that neurons, just like any other cellular activity, if they've been firing at a high rate, they develop a fatigue. They're more and more difficult to fire. So this means that in the long run, the neurons tend to fire at some average rate, sometimes fast, sometimes slow. And then the final thing goes clear back to what I consider still the best psychologist to talk about the whole system, and that's Donald Hebb. This is clear back in the days when the University in Montreal, when it was essentially a Scotch university. And Hebb was every bit a Scotchman. Okay. The key point, Hebb's rule, is that if A fires and B immediately fires afterward, then the connection, the synapse between them, gets stronger. If A fires and B does not fire, then the connection gets weaker. You could even think of it as becoming inhibitory, tending to prevent the following neuron from firing. Okay. Oh, thank you. So, the neurons in a self-stimulating group continue firing until their thresholds get to the point that they are very difficult to fire. Here's a key point. A long loop accumulates fatigue more slowly because the neurons are reactivated more slowly. Notice that I've got a set of subsets, and if I look at these subsets, each neuron in the subset fires simultaneously. Now, this has a lot to do with the way we develop language. I can think of something where I have fetch and ball, but then these longer loops allow me to put those two things together so that I can now say fetch the ball or fetch ball. And if I then look at this notion of simultaneous spikes to fire a neuron, it will take 20 of those on time step 3, but 8 on time step 6, simply because of the elapsed time. And here is a point that I consider very important, is these systems at the higher level use these various activities as building blocks to build more complex activities. So this is just like a children's set of building blocks. You have some preferred blocks around, and you use them to develop more complex things by simply putting them together. And notice the combinatorics of building blocks. And ask yourself, if you've ever watched a child, how does a child build something really complex? Notice that that castle, which any child will soon be able to build, is one of 1 billion possibilities. How did they get there? You're certainly not going to get there at random. And if I look at this, I see that, on the other hand, if I have the simple structure of 2 columns with an archway, that's 1 out of 4,000. That's something I could get by random trial and error. So if we look at the combinatorics of building blocks, what we have to understand, so to speak, is how do we get these very, very complex structures? And the claim is we get them by putting together structures that are easier to achieve to get these complex structures. And because of the way the system is designed, loops with the desired properties, because we have all the loops up to 25 length, will be there. Okay. Now ask yourself, what kind of research is going on at all these various places? And they are all over the place. You hear talk of this kind of thing, the BRAIN initiative, the EU initiative at the Max Planck Institute, Hidden Layers, IBM Albany, all of them essentially ignore the presence of loops. Now, I'm not going to talk about all these, but it's worthwhile noticing that there are 3 very different kinds of models, and these are rarely distinguished in the literature. There are what I call data-driven models, and weather prediction is a good example. We collect a lot of data, and then we try to find correlations and so on with that kind of model. A very different kind of model, and one that everybody called him Johnny, John von Neumann, used very cleverly in many ways. These are existence-proof models to show that something is possible. And von Neumann, for instance, was the first one to show that a machine could reproduce itself. Before that, all of biology, if you looked at any biology text, said that self-reproduction was a property that distinguished living organisms. So textbooks were rewritten after that, slowly but surely. And finally, there are what are called, or what I'll call, exploratory models, where I'm trying to see something about what might be possible. Now, let me talk just a little bit more about this notion of model. If I'm looking at this carefully, I have a set of things, I'll call them gauges, for making observations. And if I look at this particular example, there are 3 gauges, each of which has 5 readings. If that's the case, then this possible model has 125 states. 125 distinct possibilities if that's all I have to observe with. Now, you can think of these things. These are like the control panels on an airplane or in your car. They're the things that you're using to make the observations. The other thing that's sometimes ignored is you have to state how long, how frequent are my observations? How much time elapses between one observation and another? And this can be everything from something on a pilot's control panel. He's probably observing every second or so, maybe even more frequently. On the other hand, if I'm observing something like the planets, this may be years or centuries, or the Voyager spacecraft, even longer. So if I look at this notion of what a model is, and I'll just touch on this more technical aspect, what I have is a current observation, a set of readings I give, and then the set of changes that my model uses to predict. And if the model is valid, that should be the same as the world moving forward, whatever the basic time step is that I set. And then when I take an observation, I should get to the same place in the diagram. This is what's called commutativity of the diagram. And this is, or should be, behind every careful notion of what constitutes a valid model. Commutativity of the diagram. Now, if we use these notions to look at the development of language, we see, if we're going to do this in what I consider a proper way, there's no explicit value assigned to language. Now, this has a lot of consequences, but one of the people that I worked with for a long time, Helena Hongao, did studies. She's fluent in Swedish, in English, and in Chinese, fully fluent. And what she did was studied young children in each of these groups. And one of the main things she discovered was in each of these groups, the child did not acquire an action word. This was without exception, did not acquire an action word until they could do the action. Now this says a lot. We know that gesture is important in language. Nobody talks without using their hands, at least nobody that I know. And what this was explicit information about these 3 groups. And I just give Helena the credit that's due here. Okay. Now, we'll talk briefly about levels of consciousness. At level 0, we have the things that are wired in, the things that we get just by being human. Okay. Now, interesting kind of thing that we get that's wired in is that, and this is true of many animals too, if there is a moving object, it attracts our attention. And we both know we're looking at the same object. And all you have to do is look at the literature on a pack of wolves or something like that, and you realize that there are many animals other than humans that have this notion that they know that they're both looking at the same object. This is a major part of their planning whenever they're trying to single out something to kill. Something that happens very early, and if you watch your child when this happens, is the child at some point moves her hand in front of her face. And the minute this happens, a big smile. It's the first time that they can control the world instead of vice versa. And then you can develop these conditional rules that if there's a hand in the vision cone, move the hand to the right. I'm not going to spend much time going through all these, but we can go level by level of consciousness doing these kinds of things. And ultimately, we get to these very language-like actions. Yeah. Let's just go on. I don't want to spend much time on this. Notice that if, and this is back to the building block notion, if I in fact acquire a grammar, the combinatorics start working for me. I mean, these pieces become building blocks that I can put together and get a lot of expressions from a very small vocabulary. So if I have 10 utterances in each of these categories, there's 1,000 meaningful triples. And this is just more of what I tend to call saccades. Perhaps you remember that vision works in a very strange way. Your vision does not stare at an object. It jumps from object to object. That's the way your vision works, and you can do a lot of interesting experiments. For instance, if you have someone stare at a piece of paper with a very large letter E, say almost as large as that bulletin board over there, and you have them stare there, and you start moving the letter E in from the right, it has to be almost totally centered before they can tell whether it's an E or an F. That's part of the action of your eye. Your eye is never still. It's always jumping, called saccades, from point to point. Always. Okay. Yeah, I'm just going to go through this quickly. Let's go on to the next one. Yeah. Okay. Here's some highlights just to, this is the kind of thing that we've been doing to try to understand the acquisition of language. Signal processing and agent-based. That is one of the things that is interesting and that several people such as Bill Wong have looked at is if I look at Southeast China, there are about 200 dialects that if they were in Europe would be called languages. They're that different from one another. And a lot of what seems to be involved in this is what you could call the them and us phenomenon. If you speak my dialect, I can trust you. If you don't, then you're one of them. And these dialects persist, even though nowadays, for instance, they all share Mandarin. but the dialects are still there. They don't go away. And it is, I would claim, very much this them and us phenomenon. Okay? In the kinds of models we're trying to develop, the rules are conditional. They're if something, then do something. And that's very typical of computer algorithms, less typical of these kinds of studies. Agents build default hierarchies where you have one very general rule that's wrong a lot of the time. That's the top level of the hierarchy. Then you get rules that are exceptions to those very general rules. And they, in effect, are acquired and override the exceptions, override the default. And it turns out that if you look at this from the point of view of learning, it's relatively easy to develop default hierarchies. There are things called bridging rules. I'm not going to spend time on that. But this notion of recombination, taking pieces of rules, this is the building blocks again, to make new rules, is, I claim, very important. I'm not going to talk about the lines of research. These are some ongoing lines of research that occupy my time, usefully or not. Is that it? Yeah. I won't go into the additional details. We don't need them. Okay, so that's it.
Good. Thank you, John. Can we use your time for another 20 minutes or so?
Yes, I do believe.
A pleasure. Can I start questioning you regarding the Gell-Mann approach to this 3 orders of magnitude change in the observer's point?
Yeah.
Is it, in your opinion, the basis of emergent properties? Because I understand that what you say is basically a kind of an emergent idea.
Yeah. I think it's in many cases what's behind the emergence. And Gell-Mann's idea, which you can check out over and over again, is every time you go 3 orders of magnitude, you get a new set of laws to describe the phenomenon. And to me, that's emergence. So an important thing that's sometimes, however, ignored is when I get laws at a new level, say laws for fluid flow. Now, it doesn't make sense to call an individual molecule wet or not. But if I go up 3 orders of magnitude, I get this new set of laws that apply at this new level. So the key point is I can get new laws, like Navier-Stokes or one of the flow equations, but I'm required that they not violate the constraints imposed by laws at the lower level, 3 orders of magnitude down.
Can we go on with this issue? Because I'm so much interested in your view on emergence, because you have published books about it. It is basically what we discuss right now. It's just a kind of a perspective change in your perspective. You come further away and you see some new rules. But this is the perspective of the observer.
Yes.
What is the perspective, I would say, of the molecule or whatever it is there, out there?
Okay, I think the main point is that if I go from individual molecules, it makes absolutely no sense to call the individual wet or dry. But now, if I go these 3 orders of magnitude, then I get a new set of laws, but they dare not violate the constraints imposed by the lower level.
Now comes an issue which we discussed yesterday with Roger and Jean-Pierre. Backward causation or downward causation. because this is now a very controversial idea. It has been in the field for at least a century or more than that, and there is still a controversy here. So if you go from this level to that level, and of course the new rules, the new laws, sets of rules do not violate, of course, should not violate, can this new entity, like a molecular conglomerate or whatever, have a kind of a downward causation or backward causation type activity on the basic constituents?
And here, finally, we get to what I consider the most important activity that I'm involved with, and these are what are called agent-based models. And a simple example of an agent-based model is the stock market. Now, I look at the stock market, the activities of the agents in the market, the people who are buying and selling, determines, you know, for us, the Dow Jones average. But the Dow Jones average also influences what the individual agents do. So there's both top-down and bottom-up in agent-based models, and they change over time. So, you know, I may have an agent there that decides right now, well, if the market's going up, I'm going to buy. If the market's dropping, I'm going to sell. But that same agent, maybe a week later, and we see this happening here in Singapore all the time, may change the reaction to the market average. So agent-based models are this top-down, bottom-up thing that can change over time. So we call these adaptive systems. Complex adaptive systems is our term for this. And these, I'm trying to think, well, one thing we know by experiment is that every agent-based model that we've looked at carefully has what we call lever points, that with a small amount of action, you get big effects. Now, an easy example of that is a vaccine. If I have studied and vaccinate, say for measles or something of that sort, that simple action, before I left Ann Arbor, I got a flu shot. And that simple action can have a lifetime effect. So it's a simple lever with big effects. We have, as yet, absolutely no theory that tells us how to learn about these things.
Well, it's very similar to a philosophical question which is in the air for many decades, that simple symbols, like a very simple thing, a stop signal, can initiate a physical reaction, can initiate a whole chain of events in the physical world.
Yes.
And despite the fact that it is basically a very simple, even not a significant information content is present in it, and still it can cause a huge event. Is there any theory, or did you have, or do you have any theory about how, for instance, a symbol can have a downward causation effect or backward causation effect on the physical world?
Only in this sense of say, flu changes every year, we get new vaccinations every year, and so on. The effect, if I vaccinate a child for measles, is a lifetime effect. So there is this question of which we just have no real theory about at this point. Just what you say is the stop sign. The stop sign, in a sense, is a little bit easier because it doesn't change. So it's not adaptive in our sense of the word. But it's a part of what we need to know a lot more about.
I would love to go on, but I think I should give the word to the audience. Per.
Thank you for a very refreshing lecture, indeed. So you mentioned the combinatorial possibilities of a child building a castle from the building blocks. And this is very very little probability of reaching the goal. Can one reverse this also with respect to our perception of the surroundings? So our visual system should be able to identify any object possible, any scenery possible in the surrounding world. Now, this means that the probability, of course, of such scenes will vary according to where you are, but the number of different scenes, albeit finite, is a very big number, yet the visual system is able to see such different scenes.
I'm not sure I would agree with you there. I think what I can observe depends on, as I was trying to say it there, depends on what my instrument panel is. What is it that I'm using to make those observations? And that will determine what I can see and not see, so to speak. In particular, if I have the wrong instrument panel, well, let's see, I'm trying to think of something that typically we would not distinguish in the world around us, but it's that kind of thing that I would at least be cautious about.
Thank you again for your talk, which was very stimulating indeed. I have a very small question for informative, really. From the way you were talking about language, the way language was constructed bottom up, so the idea would be that in fact language is compositional.
Yeah.
Compositional. Now, of course, there are theories. There are two things here. There are theories of language that are non-compositional, and there are people who say that some natural languages are not compositional either. So for the first example was Hintika's game theoretic semantics. Now, my question is very simple. Do you think when you have a choice between the two, so the game theoretical thing, which is non-compositional, and your idea, which would that the other one would be more correct, though they are empirically equivalent?
This actually is leads to another kind of question. Most of you have at some time or other heard of Chomsky's universal grammar. And his notion was that it was so unlikely to have this ability to formulate a grammar that all examples were somehow wired in as parameters, as special values of a so-called universal grammar. Now, this is something that's worth watching for in research in general. What Chomsky did was definitely a step forward. It introduced the notion of theory into something that, not nice, but was stamp collecting before that. I mean, people, you know, at the time of Linnaeus, why you kept collecting all these examples of postage stamps, but you had no theoretical, this was simply what early exploration did. Okay, so Chomsky's idea was that grammars were complicated enough that they somehow had to be instances or wired in. Now, that was a big advance. It really was. The first attempt, in a very real sense, of producing something that was theoretical instead of stamp collecting. But it also soon became a huge barrier because you had no way to talk about learning or social interaction or any of these things that we consider very important in language. And so this happens more often than you might think, where the advance then becomes an obstacle.
beautiful presentation and very thought-provoking. And you introduced at several levels the notion of combinatorics. Now, this is also basic in Darwinism scheme. You know, you have variability through combinatorics or through other kind of mechanics. But then you have mechanisms which limit the variability or stabilize the variability. And this is selection. And in the brain, there are reward mechanisms which may be used to limit this variability. But in your presentation, you put reward at level 2 of consciousness, but we forgot about it later on.
Yeah.
And I think one of the missing aspects of linguistics is that even Chomsky does not take into consideration reward. And in fact, there are rewards. Because at the end of a sentence which has a meaning, a sense, then there is a positive reward for the subject,
Yeah.
which has to be taken into. So I was wondering why you did not talk about it.
Yeah, this is really this whole notion of fitness in a Darwinian sense, and I think what I get involved with when I start thinking of that is, well, we know, for instance, that there are genes in the chromosome with as many as 10,000 copies of the same gene. Now, what's the use of that? That seems a terrible waste of DNA. But if you think about it, it's very important because it lets the system explore, so to speak, without destroying the functions it already has. Now, there's a lot more to it than that because the signaling is, we now know, as we didn't used to know at all, that signals can turn genes on and off, that they can do all sorts of important actions that we used to not know about. But this is one of many examples. The thing that comes to mind is the thing that we hardly used to touch upon. Somehow we thought all of the bacteria in the gut were at the very least neutral, and now we have this whole notion of the microbiome and how important that is to all that goes on in the gut. But we have, again, very little theory about that. All we know is that it's at the present point of time, it's very hard to go ahead with the notion of species in bacteria. They exchange genetic matter so readily and so often that the notion of species becomes even difficult.
Would be interesting for us to see what makes a given level fit an achievement.
Aha.
And then you build upon it, and then there is something which is achieved, if I may say. So
Yeah.
how do you select that?
Well, again, my tendency is to think of this notion of hierarchies with exceptions. So I start out with something very simple, like, I'm trying to think of something really, it's something like all animals move. And then I realize that there are exceptions to that, and these exceptions override the original notion, and it's that, in my terms, that builds this so-called adaptive hierarchy. Yeah, meaning that if the exception occurs, then you don't do the action intended by the higher level. So, you know, well, yeah, here's an example. If it moves, flee. Now, this turns out to be a pretty good rule for a frog, because an awful lot of things that move are dangerous. But if the frog does that all the time, it's got some problems. It'll never mate. Other frogs move. It'll never eat a fly because flies move. And so that's where the exception comes in. And that at that level, then, the exception overrides in the sense that it doesn't allow the earlier rule to be executed. And if you there you can do some mathematics. You can actually do some of the mathematics. You can produce a kind of Markov process and see what the matrix looks like. It's what typically in mathematics is called a sparse matrix, almost all zeros, and so forth and so on. So there's some real both computation and mathematics you can do in that case, which is sort of interesting.
Any further comments, questions? So I'm still very much interested in your view on how nature builds up a hierarchy. You use this very nice example with the little bricks children play with, and then you can calculate very easily the probabilities of having higher and higher structures, which means is in our terminology, it would be a kind of an impossible task for nature to build such a complex system as the human brain if we believe that it is so sort of accidental, basically. But you have a clear view on how to build up a hierarchy, and you have a clear view which is in the context of evolution. That's my understanding, because you worked on it for many years. So what is your view? How is nature, let's say, limits all these almost infinite, so the limitation of the action space? How does nature or natural laws result in this sort of limitation which ends up in evolution and the human brain?
I guess what I would do, or you and I could have an argument about, is that I don't think this is a question of what nature does. It's a question of how we observe nature. So I would really make the distinction there that, as I suggested, I've got this control panel, if you want to call it that, which I use to make observations, and that's something I, as a human, could do. Now, just to really say something not really silly, but something worth considering. Now, let's change the time scale tremendously, and let's consider all the stars in our galaxy moving about and so forth and so on. Now, if I change the time scale, you know, from by a factor of what, maybe 1 billion, what would I think if I were observing on that time scale? Would it be appropriate to say on that time scale the galaxy is conscious? Since consciousness is a matter, in my terms, of interaction, and I've got this different time scale, could I describe the galaxy on that time scale in the same terms that I now describe? And in that case, notice that each sun is like a single neuron. So us on Earth are not really going to know anything about that. It's like a neuron saying that it's aware of the brain that surrounds it.
There are several books, but I think on this question, but I think Per has a view on it.
No, I don't have a view exactly on that, but there is a book out now where one physicist claims that everything that is in the universe can be described as mathematical structures. Would you agree with that?
I give you a Weasley answer. Largely, yes. And the reason I believe that is because the studies, at least that I've made of these so-called sparse matrices, seem to give me a mechanism for describing the things in terms of the method of observation.
Good. Then at least our brain and all the loops will be, we will be able to someday describe that as a set of mathematical structures.
I certainly hope so. I mean, I hope there is coming at some point a true theory of what we call complex adaptive systems. Yeah, and you know, that's a faith.
Can I come back with one more question to the former view of yours regarding the galaxies or the stars as sort of cosmic intelligence or hubs in a cosmic intelligence? We have this entropic principle. Of course, that is the strong and the weak entropic principle.
Yeah, yeah.
And of course, there are so many interesting information in this entropic principle view. But of course, the weak entropic principle says we are basically the center of the universe.
Yeah, yeah.
And then everything is somehow collapsing, not in the way of physical collapse, but in us, because we are in the center.
Yep.
And our perspective is the perspective from which we can observe the world as it is, but also we can observe our brain as this intelligent sort of creation or construction in the world. But if we take your point of view, that we remove our standpoint and we look at the universe from another temporal perspective, a billion-year or whatever perspective, and we realize there is another kind of a cosmic intelligence, do we have to change the entropic principle in a way that it will be then the cosmic intelligence principle point of view, and you still can realize there is a kind of an intelligent being here?
Yeah. I've always been, with no particular good reason, very cautious about the entropy principle. Now, here's something I can suggest. One of the very few top flight scientists that I know of that used metaphors and recorded the metaphors he used was Maxwell. James Clerk Maxwell is the only person, and if you look at his collected papers, you will see how he used simple metaphors like the tow line of a barge in a canal and so on to construct those four really elegant equations. And I can recommend to anybody that wants to see how a real scientist works and wants to see it spelled out to read that in his collected papers. It's a remarkable thing to read. It is as remarkable as, and I've been reading this and enjoying it tremendously, Lee Kuan Yew's biography. It's just one of those things where there's a person who operates in a very important and different way. And many of you have probably heard of this risk assessment, RAS, R-A-H-S, and Horizon Search that's carried on here in Singapore. You're not going to do that without loops.
A quick rejoinder to the question that Per asked here, and your answer to that, because you said it's a Weasley answer. I think you're right in giving a Weasley answer, because I would very much like to see the mathematics of causality, which goes beyond correlation. What causality really is, we are not yet ready there, I think. And I'm not even sure whether it will be, in principle, anything goes, but I'm not so sure even about in principle here. Just a quick comment.
Yeah, you know, again, it's a hope on my part, but when I see what I can do with sparse matrices and see that this is not a matter of correlation, This is a matter of conditional action. And I think when I look at that, I'm hopeful.
Okay. Thank you.
But we certainly don't have that.
John, I think we have food for discussion for the whole day, but I think we need food to continue the discussions. So let me thank you for your coming to Singapore for this event. We are really enjoying your presence here. Thank you, John.